Learning about pattern matching for switch. Traditionally, a switch statement could only match against a number, string, or an enum constant. Pattern matching for switch is a modern feature introduced in Java 21 that enhances the traditional switch by allowing you to match against types and not just constants. You will learn about type patterns, patterns and case labels, the null case label, and a few other topics. By the end of this course, you will learn everything you need to know about using pattern matching with switch. Hi, I'm a Java engineer, author, instructor, and a trainer. Come and join me in this course to learn about pattern matching with switch in Java. What you should know. This course caters mainly for Java developers. However, it can be recommended for software developers in general. Either way, if you know the basics of Java and have already programmed with Java, you are good to go. If you are new to Java, I'd suggest you take a course on Java basics first. What is pattern matching? Well, pattern matching is about testing an object against a particular structure and extracting data from that object if there's a match. In this video, I'm going to teach you how the instance of a operator is used for this. Then let's gradually move on to pattern matching with switch. For example, if there's a person object and two subtypes of it called student and employee, you can check if the person is a student, and if so, extract their marks. If not, that is, if the person is an employee, extract their salary. This can be implemented using the instance of a operator, then it would look like this. First, here's the person interface. There's the student class that implements the person interface. The student class has a property named marks, a constructor, and a getter method for marks. Here's the employee class that also implements person. The employee class has a property named salary, a constructor, and a getter method for salary. In the main class, in the getPersonData method, you use the instance of a operator to check if the object obj is an employee. If so, you have to cast it to an employee object, and then retrieve the salary from it. If not if obj is a student, you cast it to a student object, and then retrieve marks from it. In the main method, if you create a person who's an employee and pass it to the getPersonData method, then it'll print the employee's salary. This is because the object is an instance of an employee. Likewise, if you create another person, a student object, and pass it to the getPersonData method. It'll print the student's marks, and that's because the object is an instance of a student. Let's run and see. So it prints the employee's salary, followed by the student's marks. There's pattern matching happening here, but in this traditional way, you have to perform manual casting of objects. But later on, a concept known as pattern matching was introduced to be used with the instance of a operator. This was actually the motivation for pattern matching for Switch in Java 21. Let's have a look at it in the next section. Motivation pattern matching for instance of a. You saw how the traditional instance of operator works. In the traditional instance of operator, it only takes in a type like string, for example. Pattern matching was introduced to be used with the instance of operator, where it is extended to take a type pattern instead of just a type. What's a type pattern? Consider this. If obj instance of string is on the right-hand side, it's a type pattern. Here the pattern is a test or predicate plus a target and a pattern variable. By the way, a predicate is a Boolean valued function with one argument. For example, here, the instance of operator testing, if the obj argument is a string, is a predicate. Target is the argument of the predicate. For example, obj here. Pattern variable source data about the target only if the predicate returns true. For example, the pattern variable is as here, so the type pattern is string as here. Here is how it works. The instance of operator matches the target object to the type pattern in this manner. In the getPersonData method of the main class, let's write the if condition like this with the target object, obj, and then instance of a. So that's the predicate. Then type employee, pattern variable is e, so the employee is the type pattern. If it matches, return the salary formatted as a float, you get salary. Let's write the same for the student object as well in an else if block, else if budge instance of a student s. If it matches, return the marks formatted simply as a string as getMarks. Finally, in the else block, return a known person. If obj is an instance of employee, then it is automatically cast to employee, and the value is assigned to the variable e. Likewise, if obj is an instance of student, then it is cast to student automatically, and the value is assigned to variable s. If you run this, you get the exact same result as before, but you'll agree that this makes code more concise and readable. This ultimately becomes the motivation for pattern matching for Switch as well, which you'll see in an upcoming section. Evolution of Switch in Java. The switch statement has been evolving a lot throughout the many Java versions. Talking about the evolution of the switch statement, initially the switch statement supported the comparison of only primitive types like int, byte, short, and char. Later enum types were supported, making it possible to use enums as case expressions. Java 7 introduced the possibility of using string in the switch statement, making it possible to perform string matching using switch. Java 12 introduced switch expressions as a preview feature, making it possible for switch to return a value. It is important that you put a semicolon at the end of the switch block. Java 12 also eliminated the need for a break statement after each case. Instead of the break, an arrow operator was introduced. This made the syntax more concise. Switch expressions were made a standard feature in Java 14, and with this, it was possible to use switch, both as a statement and as an expression. Java 17 introduced pattern matching for switch as a preview feature. This enabled to extend switch to support any type as its target, or select expression, and case labels to support type patterns, making it more convenient to perform type checks and casts in a single line of code, similar to how it's done in pattern matching for InstanceIfa. Java 21 finalized the pattern matching for switch feature and made it a standard feature. Patterns and case labels. If you look at the basic structure of a switch, obj here is known as the target or the select expression. From Java 21, it is possible to use any type to test as the target or select expression that is any custom type. A case label of the switch can use a type pattern. Let's examine this. If you compare the InstanceIfa with the new switch, with InstanceIfa as you write, ifboj InstanceIfa string s here, the target is obj, and string s is the type pattern. Similarly in switch, now you can write switch do case string s, here the target is obj, and the case label contains the type pattern. In this code, pattern matching for InstanceIfa is used to check a type of an object obj. We can write a switch expression to replace this if errors block that uses pattern matching for switch. Let's command the if errors block. You can assign the message variable with the value returned from the switch expression like this. Then type switch. The target or the select expression is obj. Remember to add the semicolon at the end of the switch block like this. Now add the case labels. Type case, and then a type pattern can be added to the case label like this. Let's say string s, next add the arrow operator. Remember it was introduced back in Java 12 in place of break. Then let's type this statement, this is a string, and append the variable s. This will be the return value from the switch expression for this case. Similarly, you can add the other two cases as well, integer and double. So let's add them. Case integer I is the type pattern, with the I as the pattern variable, and let's say this is an integer. And append the variable I. Case double with the pattern variable d. The type pattern is double d. This is a double, and let's append the variable d. Finally, you need to add the default label. Let's say unknown type default. Let's say unknown type. Now in line number 5, assign obj with some value. Let's say 100 and run it. It says this is an integer 100. So this is how it works. A case label with the pattern applies if the value of the select expression obj matches the pattern. This is how patterns and case labels look like. Using patterns and case labels. Let's revisit the person example. In this method, get person data. I'm going to implement a switch expression that returns the matched person's data. Because this is a switch expression, I'd start by returning the expression's value. So return and then switch. The target or the select expression would be obj because we are testing the obj object. Obj the switch block. Put the semicolon at the end. Then you write the case labels. The case label can have a type pattern. That is the type, in this case, employee, followed by the pattern variable that is e. So case employee. In this case, you write the case where obj is an employee object. Next, you put the arrow operator and write the statement you want to return. So put the arrow operator. Let's get the employee salary and return it formatted as a float value. So type string format, formatted as a float value, you get salary. Similarly, you write another case label, case student s. The type now is the student, and the pattern variable is s. So in this case, if this pattern matches, you get the marks of the student and then return it formatted as a string. So after the arrow operator, let's type string format, format as a string, s get marks. If any unknown object comes, it needs to be handled by a default label by giving a default label and saying unknown type. Default label unknown type. Now let's call the getPersonData method in the main method. First, with the person pwn, who is an employee with a salary of 75, 0, call the method, passing the person object. Call the getPersonData method passing pwn. Let's assign the return value to a variable. Print the return value. Now if you run it, you'll get the salary as the output. So let's run it. You'll get the salary formatted as a float value. Similarly, you can test with a student as well. Create another person typo and assign it to a student with marks, let's say 70. Then call the getPersonData method, passing typo. Assign the return value to a string, let's print it. When you run, you'll get the student's marks. So let's run it. So you'll get the student's marks as 70. This is how you can use patterns in case labels. The null case label. What if the target or select expression object is null in a switch statement or expression? The switch would throw a null point exception. Here's how it could occur. Let's get back to a person example. Assign null instead of an employee object to person, and run the program. Let's assign null here to person, save and run the program. Well, you get a null point exception. So, how is it possible to handle null values in a switch? The most intuitive way would be to test against null values outside of switch. That would be something like this. But now, with Java 21 with the switch allowing the select expression to be any reference type, and with the case labels having patterns, the standard null check is not needed as it adds up unnecessary boilerplate code and could introduce errors. Therefore, now switch comes with an integrated null test by allowing a new null case label like this. Next, you'll learn how it is used. Using the null case label. Here it's how that null case label can be used in the person example. It's added simply as just another case label in the switch. You can add a case label as case null and the arrow operator as usual, and then return a suitable value. I'm simply returning a string value of null. In line number 4 here in the main method, person is assigned with null, so the select expression becomes null. Let's run it. Well, it won't throw the null point exception now. It returns the value that was specified in the null case label, which is the string null in this case. The behavior switch when the selector expression is null is determined by the null case label. A switch statement or expression always executes the code associated with the matching case label. So if a null value is passed to the selector expression, the switch can gracefully handle the situation if a null case label is present, and that's what happened in the demo. Guarded pattern case labels. What if you need to further test a value to see if it matches some pattern within the switch for a particular case label? This leads to writing conditional code on the right-hand side of the case label. Here's an example. Here in line number 13, if the employee's salary is greater than 100, we want to say highly paid. Similarly, in line number 19, if the student's mark is greater than or equal to 75, we want to say the grade is a distinction, something like that. By the way, yield here is a keyword introduced to switch expressions some time back to be able to return some value from a particular case. It is typically used at the end of a code block to return a value, often after performing other functions earlier in the block. Yield is usually used when curly braces are used in the right side of the case label to perform some function and multi-line case blocks like in this example, back to the switch. Checking conditions this way adds a lot of clutter to the code. Further, there might be situations where multiple conditions need to be applied to a single case. It could make things even worse. This is made possible by allowing to specify a when clause in the case labels pattern. You'll see guarded pattern case labels in action next. Using guarded pattern case labels. A guarded pattern case label contains a type pattern and a Boolean expression, which is known as the guard. The when clause is used to specify the Boolean expression or the guard condition. Here's how it's done. I'm commenting the first example and now writing it again like this. First, let's command the first example, writing a new switch expression again, return switch of obj, put the semicolon at the end of the switch expression, then start adding the case labels. First case label, case employee. Then to add the guard condition, type the when clause. When, now you can give the guard condition, for example, to check if the employee's salary is greater than or equal to a 100 0. So I'm typing get salary is greater than or equal to 100 0. Then add the arrow operator and give the expression that needs to be returned. For convenience, I'm copying it from the first example and pasting it there. Highly paid with the salary of, the salary formatted as a float. At the next case for the same case label. Let's say when the employee salary is less than a 100 0, case employee, when get salary is less than 100 0. At the arrow operator, give the expression that needs to be returned. Once again, I'm copying it from the previous example. Not highly paid the salaries, with the salary format as a float value. Next, write the pattern case label for student S, case student S, to check if the student's mark is greater than or equal to 75, type when, and the condition, S get marks greater than or equal to 75. Give the arrow operator, and then the expression that needs to be returned. That is distinction. Similarly, give another case to the same label, case student S when, the guard condition, S get marks less than 75, the arrow operator and C, not a distinction. Also add a default label default unknown type. In the main method, in line number 4, there's a person object who's an employee with a salary of a 100 0. Let's run this. When the getPerson data method is called passing that object, you get the output as highly paid with a salary of 100,000. So in this case, the first condition, which is in line number 30, was a match, and that's why you got this result. That was guarded pattern case labels in action. Ordering case labels. A switch statement or expression can have different types of case labels, ones that contain guarded pattern case labels, unguarded case labels, that is case labels that do not have guarded patterns, or constant case labels. When this is the case, ordering becomes important. Let's look at an example. In this switch expression, I move the position of the third case label to the top, which simply prints the salary of the employee. By the way, this is an unguarded case label. Let's move it to the top. Two compile errors pop up in the second and the third case labels. These two case labels are guarded pattern case labels. What does the compile error contain? Well, both contains the statement label is dominated by a preceding case label. This means the unguarded case label that I moved to the top cannot exist at that position. But why? When you place the more generic unguarded case label before the more specific guarded case label, the first one dominates the second one. It's obvious that any employee object matches the more generic condition case, employee. The switch won't further analyze the more specific case, like case employee when EGET salary is greater than or equal to 100, 0. This is why the compiler won't allow such an ordering of case labels. Let's look at another more specific example. This switch expression checks for an integer value. The first case label is a constant case label that checks if the integer value is 42. It's followed by another case label that has a guarded pattern case label that checks if the integer has a value of 1. Finally, there's an unguarded case label that just checks if it is any integer. If you just happen to move the constant case label, case 42, after the pattern case label, case integer I that checks if the value is any integer, let's move this case label after this case label. The compiler gives the same error as before. Label is dominated by a preceding case label. This means the pattern case label, integer I, dominates the constant case label, case 42, by matching any integer. It doesn't give a chance for switch to further analyze a more specific case, like case 42. Therefore, you should place the more specific or precisely matching case label, case 42, before the more general case label, case integer I. Like this. Looking at another example, in this example, the second case label, which is a constant case label, is unreachable. It says switch label alone is unreachable because the first guarded pattern case label will always match for any string value. Then the case hello is never reachable, therefore, it should be placed before the guarded pattern case label, which makes it a reachable case label. Move it before the guarded pattern case label. So, looking at all these scenarios, a simple, predictable and readable ordering of case labels would be to place any constant case label before guarded pattern case labels, and to place guarded pattern case labels before unguarded pattern case labels. In other words, more precisely matching to least precisely matching. Exhaustiveness of a switch block. Exhaustiveness. What is it? In terms of a switch statement or expression, it means that all possible values of the target or select expression must be handed in the switch block. Once again, target or select expression means the thing or object being checked by the switch. Exhaustiveness means, in other words, that it has to maintain the fact that successful evaluation of a switch expression always must yield a value. For normal or non-pattern switch statements, this means switch statements that existed prior to Java 21. This is enforced by including a set of conditions or cases with all possible values. For pattern switch expressions and statements, this can be via type coverage of switch labels in a switch block, because types are involved here. The type coverage of all the switch labels in the switch block in combination determines if the switch block is exhaustive with all possibilities of the select expression. For example, if you have a switch expression like this with a single case label, the compiler says that the switch expression does not cover all possible input values. Adding a few more cases, let's add 2 more cases, still gives the error. This is the meaning of the earlier statement, that is, the type coverage of all the switch labels in the switch block in combination determines if the switch block is exhaustive with all possibilities of the select expression. It's not practical to do it. This is why a default label needs to be added. Having a default label can make a switch statement or expression exhaustive. So adding the default label, the error disappears because the compiling is satisfied that the switch is exhaustive now. However, it is also possible to achieve exhaustiveness without the use of the default label, that is, if the type of the select expression is a sealed class or an interface. First of all, what is a sealed class or an interface? It is a special type of class that restricts which other classes can extend or implement it. It enables the enforcement of specific inheritance rules and improves code safety by providing a more controlled hierarchy. Let's look at an example. The animal interface in my_1 is a sealed interface, which permits only implementations of types dog, cat, and bird. It has a method, makeSound, so the classes implementing the sealed interface can be defined like this, with the makeSound method implemented, the dog class in my_5 with the makeSound method implemented in my_8, the cat class implemented in my_13 with the makeSound method implemented in my_16, the bird class in my_21 with the makeSound method implemented in my_24. The final keyword in the implementation class denotes that these classes cannot have subclasses. For this example, you won't need them to have subclasses. In my_37, a method, getSound, is implemented, and in it, a switch expression is implemented. In the switch expression, you can have pattern case labels like this: dog G, cat C, bird B. In this case, the type of the select expression, animal, is a sealed interface, so the type coverage check have taken into account the permitted types, dog, cat, and bird. So simply, if there are pattern case labels, like dog G, cat C, and bird B, you've achieved exhaustiveness in the switch expression. So in this example, since there are 3 pattern case labels covering all 3 permitted types, the switch becomes exhaustive, and therefore, a default label is not needed. Now if you try to make the animal interface a non-sealed interface, let's remove the sealed keyword and permits. Again, the switch starts giving the same error for exhaustiveness. It says the switch expression does not cover all possible input values. Then to make it exhaustive, you have to use the default label. So a switch isn't exhaustive unless you cover all possible types, as with using sealed classes or interfaces, or otherwise, you should include a default label. Using record patterns with switch. Before learning about record patterns with switch, let's quickly look at what a record is. The record feature was first introduced in Java 14, and eventually became officially available in Java 16. A record is an immutable data class that requires only the type and the name of fields for it to be declared. If you are wondering what immutable means, an immutable class in Java means that once an object is created, its content or data cannot be changed. For example, all wrapper classes, like integer, boolean, byte, short, and string in Java are immutable. So a record is similar to these because it is immutable. All the boilerplate code, like equals, hash code, to string methods, as well as getters and setters and constructors generated by the Java compiler. By default, the fields in a record are final. This is what makes a record immutable. Records are great as data transfer objects or data carriers. Having talked very quickly about Java records, this is an example of a record. In line number 1, there's a sealed interface named shape. By now you know that a sealed interface is what permits to only create subtypes of a permitted set of types. In this case, the shape sealed interface permits the creation of subtypes circle, rectangle, and triangle. A subtype can be a final class, or a sealed or an unsealed class or a record. In this case, we create 3 records, circle, rectangle, and triangle in line number 3, 4, and 5 that implements the sealed shape interface. Now if you want to find out the details of a shape, like the radius of a given circle, the length of a rectangle, or the base and height of a triangle, traditionally you would write code that looks like this with an instance of keyword. But now with record patterns for switch, you can do it in a better way. With pattern matching in switch together with record patterns, you can now make this code more concise and readable. The record can be used in the switch expression, where it allows you to deconstruct the record directly and enable access to the data within them, making the code more concise and readable. Now let's write the earlier code using record patterns. I'm commenting out the earlier code and pasting this code. So you would write code like this. For example, circle int radius. Radius is the property of the circle. The switch automatically allows to deconstruct the record to access directly its radius property within the case label. So within that case label, it's possible to access the property. In the next case label, there's the record rectangle. It has two properties, length and width. The switch automatically allows you to deconstruct the record to be able to access the length and the width properties within the case label. It is the same thing with the triangle. This makes code more concise and readable than writing a bunch of if statements with instance of and having to perform casting. So this is how record patterns with switch can make your life easy with the ability to deconstruct the record directly. Next steps. Well done on completing this course, and thanks for joining me. As next steps in your learning journey, you can practice what you've learned by applying your knowledge to more scenarios. If you would like to find out more about pattern matching for switch, you can check out GIPOR JIDCL Enhancement Proposal 441. If you need to find out further enhancements in Java, you can check out Oracle's Java documentation or OpenJIDCL.